You know, I was stuck in traffic this morning. Same old stretch of road, same orange cones, same guy in a high-vis vest, just staring at a hole in the ground.
Ah, the universal experience.
It's been 3 months. I feel like I've watched his kids grow up just by driving past. It feels like a law of nature, right? Big things have to take a long time.
They're supposed to. We're conditioned to think that way. Infrastructure means slow, painful, multi-year commitments.
Exactly. But then I started digging through this stack of sources you sent over about China's recent megaprojects, and honestly, it feels like I'm reading science fiction.
It does sort of redefine your whole sense of time, doesn't it?
It totally shatters it. I mean, we were talking about replacing massive bridges over a weekend, hospitals just appearing in days.
Pushing tunnels through ground that's basically soup. It's wild stuff.
It is, but the mission for this deep dive isn't just to, gawk at the speed. Anyone can watch a time-lapse video and say, wow.
Right. We want to understand the mechanics of it, the engineering, the logistics, how these impossible timelines become, well, actual reality.
We want the how. Is it just throwing a million people at the problem? Or is there like a fundamental shift in technology going on here?
It's a bit of both, but you hit on it. The technology, specifically this move toward prefabrication and digital modeling, that's the real game changer.
So it's less construction and more assembly.
That's the perfect way to put it.
Okay, before we jump in, just a quick note. The sources we're looking at cover some massive projects. We are looking strictly at the engineering, the physics, and the project management reported here.
Exactly. We're here to geek out on how you move a 1,300-ton slab of concrete without dropping it.
Not the politics behind it.
We're all about the nuts and bolts. Literally.
Okay, so let's start with that speed. The project that made me, physically squint at the paper to make sure I wasn't misreading the number. The Sanyuan Bridge in Beijing.
Yes. A classic case of what you might call surgical infrastructure.
So set the scene for us. This is a major artery in Beijing.
Huge. Over 200,000 cars a day.
Right.
And the bridge is sagging, it's unsafe, it has to go.
Which in any other city is a 6-month, maybe year-long nightmare of gridlock.
Minimum. And for a city with Beijing's traffic density, that just wasn't an option. It would have caused a total cascade failure of their transport network.
So the timeline they proposed was
43 hours.
43 hours. I can barely assemble a desk from a flat pack in 43 hours. How do you delete a bridge and just paste a new one in less than 2 days?
You have to completely change the sequence. I mean, normally you demo the old one, clear the rubble, build the forms, pour concrete.
And then wait for it to cure, which is the slow part.
Right. It's literally watching paint dry's boring cousin. So here, they did everything in parallel. They built the entire new bridge.
The whole thing.
The whole 1,300-ton span. They built it in a parking lot nearby before they even touched the old bridge.
Okay, but then you've got a new problem. You have this monster slab of concrete sitting in a parking lot. How do you even move it?
You bring in the Shen 2O.
That sounds like some kind of mythical beast.
It pretty much is. In English, it's something like divine support. It's a specialized modular transporter. We're not talking about a truck.
What are we talking about?
A platform with 96 independently controlled wheels.
96.
Yeah, and that's critical because with 1,300 tons, if you don't spread that weight perfectly, you just punch a hole in the road. These wheels spread the load like a snowshoe.
So they cut out the old bridge.
Which was terrifying in its own right. They sliced it into 27 chunks. The heaviest was 139 tons.
Which is, what, twice the weight of a blue whale?
Something like that, yeah.
Hey.
And they're lifting these giant pieces off a structure that's already failing. It's like high-stakes Jenga.
And once it's clear, the Shen 2O just drives the new bridge in.
It rolls it right into place. But here's the crazy part. They have to set it down on the existing pillars. And the tolerance for error is millimeters.
Millimeters?
If you're off by an inch, the whole thing is structurally unsound. So they're using lasers and GPS to guide this 1,300-ton mass into place. It's like watchmaking, but for a megastructure.
And they hit the deadline.
43 hours. Paved, painted, and traffic was flowing again.
That really drives home that idea you mentioned. Assembly, not construction. The site is just for installation.
Exactly. And we see that same philosophy at the Longyan train station.
The 9-hour upgrade.
Right. An active station they had to prep for high-speed rail.
The video of this is insane. It looks like an army descending on the tracks. 1,500 workers.
It's organized chaos. It's like a construction ballet.
Yeah.
You've got all these excavators and people in a tight space. If one team is 10 minutes late, the whole chain falls apart.
And again, they weren't building track piece by piece.
No, way too slow. They prefabricated entire sections of track with the sleepers, the ballast, everything off-site. They just cut out the old stuff and dropped in these giant Lego pieces.
The part that got me wasn't the heavy lifting, though, it was the wiring.
The signaling system.
Yeah, they had to rewire the whole thing that stops trains from hitting each other. In the middle of the night, outdoors, with 1,500 people running around. That's intense.
It's military-grade coordination. The electricians were literally working in the gaps between the heavy machines. And by dawn, it was live, tested, and ready.
Incredible. But sometimes speed isn't just about efficiency, sometimes it's about survival. Which brings us to Huashinshan Hospital.
The Wuhan Project.
Early 2020, the pandemic is just starting. They need isolation wards, and they need them yesterday. The headline is 1,000 beds in 10 days. My first thought was, okay, so it's basically a field of tents.
And that's the misconception. This wasn't a tent city. This was a 34,000 square meter facility. It had complex stuff like negative pressure ventilation, full plumbing for every room. It was a proper hospital.
How's that possible in 10 days? Even with prefab, the plumbing alone seems like it should take months.
Two key things. First, the supply chain was ready. The sources say authorities had actually invested in factories for emergency response materials months before this happened. They had wall panels and plumbing units just sitting in warehouses.
So they weren't designing from scratch.
The parts were there. But putting it all together, that's where the digital twin comes in.
Okay, unpack that for me. It's a buzzword I hear a lot.
In construction, it's a total game changer. Before a single shovel hit the dirt, they built the entire hospital in a 3D simulation. But it's more than a drawing. It's a database. It knows that this specific pipe needs to go through this specific wall at this exact coordinate.
So it finds all the mistakes before they can happen on site.
Exactly. You can't have 7,000 workers on site and have a plumber walk up to a framer and say, hey, you put a stud where my pipe is supposed to go. That argument wastes 20 minutes. You don't have 20 minutes on a 10-day build.
So every part just clicks into place.
With minimal on-site adjustment. They were laying 2,500 square meters of floor plan a day. That's like building a big suburban house every couple of hours.
That's just a different reality. Which brings us to a different challenge. Speed is one thing, but pure brute force scale is another. The hydro project.
Ah, yes, the monsters of the industry.
Baihetan hydropower station. The numbers here are just hard to wrap your head around. 16,000 megawatts.
For context, that's enough to power a medium-sized country.
And it's all from just 16 turbines. Each one is a 1,000 megawatt unit, the largest ever built.
And they're almost 97% efficient.
How do you get a machine that huge to be so efficient? I feel like friction alone would just eat up all the energy.
It's all in the seals. The source mentioned a partnership with SKF. On turbines this big, even a tiny bit of water leakage around the blades is a huge efficiency killer. They managed to cut the leakage down to 1/10 of the industry standard.
So almost every drop of water is doing work.
Exactly. But the dam itself is maybe the real marvel. It's a concrete arch, 289 meters tall.
That's a 100-story building holding back a river.
And holding back 16.5 million tons of pressure. The problem with pouring that much concrete is heat.
As it cures.
Yeah, concrete curing is an exothermic reaction. It gets hot. If it gets too hot, it cracks. And a cracked dam is a failed dam.
Catastrophically so.
So they embedded thousands of thermometers and cooling pipes inside the dam as they poured it. A computer system monitored the temperature in real time and pumped cold water through the pipes to keep the cure perfectly even.
The concrete had its own climate control system.
It had to. It's the only way to build at that scale without fatal flaws.
And of course, you can't talk dams without mentioning the Three Gorges, just the sheer size of it. But the part that caught my eye wasn't the power, it was the elevator.
The ship lift.
Yeah, I knew about locks, the little staircases for boats, but this is a full-on elevator for ships.
It's all about efficiency. The normal locks take about 4 hours to get through. If you're a smaller ship, you don't want to wait that long. So they built this massive lift that just carries the ship, water and all, straight up and over the dam.
How much weight are we talking?
The total lifted mass is around 15,500 tons.
That's just showing off at that point.
It's practical. It cuts the transit time down from 4 hours to 40 minutes. Time is money in shipping.
Fair enough. Okay, so we've covered speed and scale, but what happens when the planet itself fights back? The Humeling Tunnel.
Ah, the tofu tunnel.
The nickname alone makes me nervous. So this is in Gansu province. What is this loess soil?
Loess is basically wind-blown silt. It's super fine. And in this area, it was saturated with water. When you mix loess and water and then you disturb it, say with a giant drill.
Oh.
It becomes thixotropic.
Which means?
It liquefies under stress. Think of it like quicksand. You drill into it, and the tunnel face just turns to soup and flows into your machine.
The source said international experts, some top German engineers, basically gave up on it, said it was impossible.
They couldn't stabilize it. There was one section, just 173 meters long. Less than 2 football fields. Took them 6 years to get through it.
6 years? For 173 meters, that's centimeters a day.
On some days, yeah. This is the exact opposite of the train station. No brute force. They had to use a technique called vacuum dewatering.
So they're literally sucking the water out of the dirt ahead of them.
To turn it from soup back into solid earth, just so they could excavate a few inches at a time without it all collapsing.
That's a humbling contrast to the 43-hour bridge. Sometimes geology just wins.
It definitely calls the shots. But they did finish it. They engineered a solution instead of rerouting.
Speaking of tough geology, the Hong Kong-Zhuhai-Macau Bridge, 55 kilometers long.
The longest sea crossing in the world. And it's a hybrid. Bridges, artificial islands, and a tunnel.
But they didn't drill the tunnel, right?
No, the seabed was too soft and inconsistent. So they used an immersed tube method. They built the tunnel in giant 80,000-ton concrete sections on land.
80,000 tons? That's like a concrete aircraft carrier.
Pretty much. They'd float them out to sea, sink them into a trench on the seafloor, and then seal them together underwater.
An underwater highway made of sunken blocks.
Exactly. And the source mentioned a nice environmental reason for it.
The dolphins.
Yeah, the Chinese white dolphins. Their habitat is right there. A huge suspension bridge with hundreds of pillars would have wrecked it. By putting that section of the crossing underwater, they minimized the footprint.
That's a pretty elegant solution. So now we're seeing this capability get exported, right?
Right. Zooming out, there's the Meroe Dam in Sudan.
And this is a prime example of that package deal approach you hear about.
Totally. It's a massive 9-kilometer-long dam on the Nile. But a dam is useless if the power is just stuck in the middle of the desert.
You need the grid.
So the project wasn't just the dam. It included laying 1,500 kilometers of transmission lines straight across the Bayuda Desert. They bring the entire logistical chain with them.
Okay, before we wrap, we have to talk about the one project that gives me vertigo just reading about it. The Zhangjiajie Glass Bridge.
The psychological thriller of infrastructure.
A glass-bottom bridge, 300 meters in the air. Why? I mean, just why?
Tourism, adrenaline. But the engineering needed to make people feel unsafe, while actually being perfectly safe, is fascinating.
The glass is super thick, right?
Triple layered. 15 millimeters thick. To prove it was safe, they drove a 40-ton truck over it. They even let people try to smash the top layer with sledgehammers.
And it held.
The top layer cracked, but the structural layers underneath were fine.
My big fear wouldn't be falling through, it would be the wind. A suspension bridge that high has to sway.
It does, and that causes panic. So to dampen the sway, they hung these giant 500-kilogram glass balls underneath the bridge deck.
Wait, glass balls?
They're tuned mass dampers. When the wind pushes the bridge one way, the balls swing the other way, and it cancels out the vibration. It keeps the bridge feeling stiff.
So giant glass marbles are keeping you from getting seasick 300 meters in the air.
Basically, yeah. It's designed to feel invisible, so you think you're floating, but structurally, it's an absolute tank.
I think I'll stick to the photos on that one. Okay, so looking back at all this, bridges, hospitals, dams, tunnels, what's the common thread? What's the secret sauce?
I think it really comes down to 3 things. First is standardization and prefabrication. Moving a work from a chaotic site into a controlled factory.
Turning building into assembly.
Right. Second is digital integration. Using that digital twin, using real-time sensors like in the dam to make sure that when you move that fast, you don't break things.
And the third?
Just massive mobilization, the ability to coordinate logistics on a scale that's almost military. Getting that 96-wheel transporter or those 7,000 workers to the right spot at the exact right time.
It really challenges our own acceptance of how things are, doesn't it? We just accept that a hospital takes 3 years to build. We accept a bridge repair takes 6 months.
These projects prove those timelines aren't laws of physics. They're choices, or maybe limitations of our current systems.
And I guess that's the thought I want to leave everyone with.
Yeah.
If the engineering exists to snap a bridge together in 43 hours or get a hospital running in 10 days, what's the real bottleneck in our own neighborhoods? Is it money? Is it bureaucracy?
Or is it just a lack of imagination? It's a question worth asking the next time you're staring at that same orange cone that hasn't moved since March.